in the last class we have seen that electrical quantities and mechanical quantities can be equivalenced, and let us start by just recapitulating where we were. We saw that in mechanical domain the basic coordinate is position or displacement from some datum position, and its electrical equivalent would be charge. The rate of change of position is velocity. So, velocity is equivalent to the rate of change of charge, which is current. Okay. Then acceleration is rate of change of current, di dt. Force is equivalent to electromagnetic force. What else? Mass is equivalent to inductance, in the sense that mass has the property of resisting change in its inertial status, inductance has the property of resisting any change in current. Then you have spring constant, K, that is equivalent to 1 by C, 1 upon capacitance. Good. The damping constant or frictional coefficient is equivalent to resistance. Finally, the two things I forgot to talk about in the last class. In mechanical domain, there are two types of energy, the kinetic energy and the potential energy. So, let us see what they are equivalent to. The kinetic energy is how much? Half m v square. Half m. M is proportional to m is equivalent to L, V is proportional to I. So, half L I square, it becomes equivalent to what is half L I square? The energy stored in the inductor. So, kinetic energy is equivalent to the energy So, if in any circuit there are 3 inductors, the kinetic energy or equivalent of the kinetic energy in that circuit would be the total energy stored in the 3 inductors. Potential energy then would be equivalent to the energy stored in the capacitors. Visible? So, this sort of completes the story of the equivalences. It is not easy or common sense to see that the energy stored in the inductor is actually has the property of a kinetic energy, and the energy stored in the capacitor has the property of potential energy, but you should know that. That was essential content of the first class, last day's class. So, let us start off from there. We said that the Newton's method can be written simply as force is equal to mass into acceleration. So, we will write it as the mass into acceleration in the left hand side, because that is the derivative part. So, m q double dot is the mass into acceleration is equal to what? Whatever the force is. Now, this force we said has two components. One, something that is impressed from outside, either it can be some externally applied force or it can be a force applied by the other elements of the system. For example, if it is sliding against something, two bodies are sliding against each other, then one body experiences a force applied by the other body, which is also part of the system. For that body, that this force will, this frictional force will have to be included. If this body is connected to another body by means of a spring, then because of the spring, the other body pulls with some force. So, that is also included here. So, all these forces are to be included. So, this has to include the externally applied forces, it has to include the forces between elements which are connected by springs, forces between elements which are connected or interacting with the help of frictional elements, also, and which is crucial, the constant forces. So, let us just recapitulate what we said about the constant forces. Most of the motions of bodies are constant in some way. As we showed the example, that if you have a pendulum like this, then its bob is constrained to move on the surface of a sphere, right, and that happens because the constant applies a force on the body. So, this force then has to be included. If you have a surface like this and you release some kind of a body here and it slides down, why does it follow this particular equation? Because it is acted on by a force, that is the constant force. So, when you write the Newtonian equation, then these constant forces have to be included, clear. That is why the Newtonian equation will have to be written as plus F c, these are the constant forces. And if you have n number of such bodies, for each body then it will have to be written with a subscript, right. For each body you will have an equation like this, for all the n bodies you will have equations like that, clear. Now, we need to say a few more things about the constants. Constants can be of a few different kinds. See, these constants, let us, how can we mathematically express the character of these constants? What kind of constant is this? Here we can express the constant as some kind of a function, some kind of a algebraic equation, this one, can we not? So, it was originally a 3-dimensional space and we can then express a equation which will restrict it to a lower dimensional space, clear. So, that requires one equation to be written. What is the form of that equation? It will normally be of this form, some kind of a f of, if there are many such variables. So, you will write x1, x2, x3 and so on so forth equal to 0. Okay. In this case, the position is given by x1, x2, x3 and a specific equation relating this x1, x2, x3 equal to 0 gives the constant equation, right. In general, this might also be, this function might also be dependent on time. You might imagine that this is being moved. You might imagine that this is being moved. So, in general this might also contain time. Now, any constant that can be expressed in this form is known as holonomic constant. Remember this word. is called holonomic constant. Some holonomic constants do not need this term t, that is it is independent of time like this, and some holonomic constants will need additionally this concept of time, the dependence on time, but both are holonomic constants. You can easily see that the holonomic constants actually reduce the dimensionality of the system, right. For example, here the bob is constrained to move on the surface of the sphere, and therefore, we can, as we will see, we can define a new coordinate system on the surface of the sphere, and that is actually what we do. For a pendulum, it will be stupid to write in terms of x, y, z. It will be far more logical to write in terms of theta and phi, spherical coordinate system. Why? Because what we are actually doing is that we are writing in terms of a lesser, smaller number of coordinates, constrained to the constant surface. Remember that. Okay. So, holonomic constants are actually our advantage. Holonomic constants are our advantage. We will have to learn how to take advantage of that in a systematic way. In case of the pendulum, just by looking at it, by applying our common sense, we saw that okay, no, we do not need to use x, y, z, we can better use theta phi, but that is observation. There has to be some kind of a systematic way of going about it. That is what we will learn. But let us, a natural question is, can there be a non-holonomic constant? A constant, but non-holonomic nature. Yes, that there can be something that cannot be expressed in this form. Imagine in your hostel, do you play carom? The bodies are constrained because they have to remain within that boundary, but can you express their equation by means of like this? No. Still it is a constant. That kind of a constant which is expressible as an inequality, not equality. Here is equality, right? But a body constrained to move within the boundaries of the carom board is given by a inequality. This point, that point, this point let it be 0, that point let it be L. So, x coordinate is constrained within 0 and L, it is inequality, right. That is a non-holonomic constant. Billiard is a non-holonomic constant. If you have a container and molecules moving within that, they are constrained by a non-holonomic constant, because they have to be within that. And even very simple situations can give rise to non-holonomic constants. Imagine very interesting example. Suppose you have got a line and some body that can move on this line, and there is another body that can move on this line. One dimensional problem, not a difficult thing at all. So, it is the q coordinate of this body and that body, and they are free to move. Are their motions constrained by anything? Yes, of course, they cannot occupy the same position. Their bodies, they cannot occupy the same position. Now, imagine if I plot their okay, what will be the configuration space in this case? Configuration space, we introduced that concept in the last class. The minimum number of coordinates, position coordinates that you need in order to express the complete positional status of the system. The system contains two bodies, so you need two position coordinates, and the configuration space will be then q1 and q2. q1 is the position of this one and q2 is the position of that one from something. Okay. And then in this q1 q2 space, these bodies will just move around. Their motion, that means in the q1 q2 space, the motion of these two will be given by some kind of a trajectory. Okay. Notice I am not talking about the trajectory of this one given by some orbit and trajectory of that one given by another. I am talking about then in the configuration space the total positional status of the system consisting of these two bodies given by a point. Okay. Now, that point can move around like this, which would then mean, supposing it is here, which would then mean that the position of this fellow q1 is here minus something and position of that fellow q2 is plus something. Okay. So, this is a configuration point. This is a configuration point. Is it clear that here we are not talking about individual positions, but their collective position, the position coordinate of the whole thing represented graphically in the configuration space. Now, notice this line then becomes a forbidden line. This line means what? Q1 and Q2 are the same 45-degree line. Q1 and Q2 are the same means that is a forbidden state, they cannot take the same position, which means that in the configuration space this configuration point can either wander in this side or in this side, but cannot cross, right. So, it can go like this, no problem, fine, but it cannot cross, because crossing would mean that at some point of time the two occupy the same position. That means, within the configuration space then the point is then constrained. What kind of constraint is that? It is an inequality constraint, it cannot take this value, either it is here or here. So, it is also a non-holonomic constraint. Okay. Fine. So, the non-holonomic constants, as you can see, that does not reduce the system dimension, holonomic constants do, and fortunately most of the engineering systems have some kind of holonomic constants. So, it will be more important for us to understand or to be utilize the advantages of holonomic constants. So, let us pay some more attention to that. First, in case of the simple pendulum, if you express in terms of x, y, z, what is the holonomic constant equation? It is constant to lie on the sphere. How is it expressed as? It will be x1 square plus x2 square plus x3 square is equal to L square, assuming this to be the origin. It will be trivial to move the origin to this point, because that will be simple first step that anybody would do. So, this minus L square is equal to 0. I am expressing at some function of x's equal to 0 in this form. Okay. Now, suppose this point is moved as a function of time, then what? Then also at every position, supposing it is here, then also from that position it will be a surface of a sphere. Again it moves here, and from that position it will be a surface of a sphere. So, essentially what is happening is that this if it is moved like this, then also it is a constant, but what kind of constant can we express that? This is the x direction, suppose. In that case you will say that is x1 plus that function of time, this square plus x2 square plus x3 square minus L square is equal to 0. That will be the constant equation. Notice that this is expressed as f x j comma t equal to 0. Sorry, this is expressed not as this, and this is expressed as f x j comma t is equal to 0. uh, actually they have some names. You will find in textbooks that this has a name, that has a name. This name is scleronomic constant, and this name is do not be scared by the names. I will not shoot you if you forget these names. But still, why am I writing it? Because in books, if you come across these words, you should know what they are. They are not fruits hanging in the trees that you can pluck and eat. They are specific names of specific types of constants. You should know, that is all. So, if you come across these words, you should be able to say that these are specific types of constants. But if you forget, if this type, what is the name? Okay, there is no problem about it, because everybody cannot remember everything, I know. So, these terms were coined, these are coming from Latin, and still these are the terms used. So, I will go by assuming that you will forget these names, and I will not take that as a big sin. Whatever it is, the point is these are the names. When you come across them in the textbooks, you should know what they are. So, we have seen that there are two types of constants in the main: holonomic constants and non-holonomic constants. Holonomic constants offer the advantage that you can, if you are clever enough, reduce the system dimension. In case of non-holonomic constants, you cannot do that. So, if you have non-holonomic constants, you are forced to use the old set of coordinates. For each body, 3 coordinates x, y, z. So, normally if there are 3 bodies, then how many coordinates will be there? 9 coordinates. If it is constant by a non-holonomic constant, you will have to use all the 9 coordinates. But if there is one holonomic constant, then the system dimension reduces by 1. If there are 2 holonomic constants, the system dimension reduces by 2. If there are 3 holonomic constants, so it goes on reducing. Imagine here you have the equation as this, right? That is one equation that makes the dimension 1 less from 3 to 2. But imagine that if it is a planar pendulum, then there is one more constant equation, that is, say, y is equal to 0, or x2 equal to 0. So, x2 is equal to 0 is what? Is a constant equation, then it is also in this form, x2 is equal to 0. Geometrically, what are you doing? Here this equation, one constant equation defines some kind of a subspace. The second constant equation defines another subspace, and then the ultimate constant is what? The intersection between the two. Okay. Since it is the intersection between the two, then the system dimension reduces by the number of holonomic constants. Okay. So, the system dimension reduces by a number of holonomic constants, and that obviously is a major advantage. Now, the point is that in the classical Newtonian method, there is no systematic way of utilizing this advantage. Let me illustrate by doing it for the simple pendulum. If you write the equation for the simple pendulum by the Newtonian way, x, y, z, do it, write the equation. You have the simple pendulum, here we will take the theta, here there will be a tension working T, here there will be mg working, fine. So, x coordinate, y coordinate and z coordinate, clear. If we draw the free body diagram, the way I shown the D'Alembert's way, then we will have to do two free body diagrams, along the x coordinate, along the y coordinate. Along the x coordinate, what will be the equation? In this direction, what is the pull? Theta is here, t sin theta, t sin theta. That will be counterbalanced by mass into acceleration in that direction, m x double dot, right. So, that is the free body diagram in the x direction. In the y direction, here is a pull working, that is t cos theta. So, t cos theta. In this direction, mg, right. So, you have the mg minus t cos theta working, and naturally there will be a component of the acceleration, mass into acceleration, m y double dot. That will be the free body diagram. Simply equate, you have the equations given. So, m d2 x dt2 is equal to t sin theta, m d2y dt2 is equal to mg minus t cos theta, and z direction, m d2z dt2 is equal to 0. There is nothing working in that direction. So, the Newtonian set of equations are like this. Okay. How many equations did you need? 3. How many coordinates did you need? 3. And also t becomes included in the equations. Do you know how much t is? You do not know really. And as it swings, the t varies all the time. So, here is something that is very difficult to know, but it has gone into the formulation. So, that is the problem of the Newtonian method, that the constant force gets into the formulation. And in case of a situation like this, will you be able to write down what the constant force is? Very difficult. So, it was realized soon after Newton that something has to be done about the constant forces. We cannot write down the equations properly, or you can really solve the equations if the constant force get into the system equations. That is one difficulty. Second difficulty is that if you have say many bodies interacting by means of something like so this is a frictional element or the another spring element. So, like this, then all these mutual interactions have to be considered. On this body, not only the force due to gravity, but also all these forces have to be considered, and they are vectors. Can you see, even if the system is so simple, only 3 bodies with this, writing down the differential equations would be mess, because all these have to be written in vectorial terms. All these will have different directions, and then the Newton's equation itself will be a vectorial equation, will be tough. And I am sure if I give you this problem in an exam, you will fail. That is why we need to do something about these forces. What are these forces? Out of this, there was a problem with this one. Out of this, there was also a problem with this one, because these are all vector forces. Okay. Something needs to be done to that, something needs to be done to simplify that. And thirdly, the Newtonian technique does not offer any direct way of reducing the system dimension. These 3 were recognized as major practical difficulties with the direct application of the Newton's method. True, Newton gave the basic idea of writing the differential equation, and after we had the Newtonian approach, that is when we started being able to solve the equation for the Mars, for example, it was possible to write down a differential equation for the motion of the Mars, calculate the initial condition, solve it, and then predict where it will be. It actually was there. So, all these major advantages came because of the Newton's laws, but these were the practical difficulties. We ultimately need to write down the differential equations. So, within 100 years after Newton, the solution of these practical problems came, and they are very valuable when we try to write down the differential equations for engineering systems. So, let us try to learn how these practical difficulties were overcome. That will need a bit of foray into mathematics. So, do not get scared about that. Most of you are more or less conversant with maths, in fact, at home with maths, I would say. So, do not get scared about that. So, let us recognize the first problem. The first problem was that there were constant forces that were troublesome. Here we had to write down the equations using the constant forces, and that is a mess. If there are many constant forces, then it will be even more mess. About a century after Newton, people like Lagrange, D'Alembert, Hamilton, they produced this technique. They noticed that there is a speciality of the constant forces. They do no work. Have you noticed? The constant force is in this direction, and this fellow is moving in this direction, perpendicular direction, and the constant force is doing no work. So, instead of writing the equations in terms of forces, if I write the equations in terms of the work done, we are through. We can straight away get rid of the constant forces, can't we? So, the next stage was to write down the equations in terms of the work. Work done by the constant forces would be 0. Now, that gave rise to a very solid way of writing down the equations, but let us first start with the Newton's laws by rewriting the Newton's laws. The Newton's equation would be m for each mass point from a coordinate system, every mass point will have a r, right, a vector, another vector and r. So, r1, r2, third mass point, r3 and all that. So, for each one mj rj double dot, this r is a vector. How do I? Normally in print we mark that by a bold face, but let us put a small arrow overhead to mean that it is a vector, is equal to f j, which is a vector, plus f c j. For each mass point we will have equations like this, and then we can add them up to obtain equations of this form. I will put this one here to keep the right hand side only with the constant force, so that we can eliminate that later. We will write it as add them up, all the equations. So, sigma j is equal to 1 to say n number of bodies, m j r double dot j, this term minus this minus f j, this is equal to the total number of constant forces added together. So, that is the Newton's law, right, and we are now trying to get rid of this guy. We have just mentioned that the constant force does no work. Is it always true? I will come back to this. Imagine this situation. Where is the constant force? The tension in the pulley. Does it do no work? No, it does. For this one, if it moves by q amount, then it does work, and on this fall also it does work. But then overall, taking the system into consideration, they cancel off. Can you see that? So, it is not always true that the constant force does not do any work, but overall it will sum up to 0, and that is why we needed to sum up. We did the sum because of that. We need to get rid of the constant forces. So, the constant force in some situations may do some work, but ultimately when summed over all the bodies in the system, that gives 0. That is one situation. Suppose a body is sliding down a surface, the constant force is acting like that, right. It is always sliding down in a direction that is orthogonal to the constant surface, constant force, and therefore, you are happy that there is no work done by it. But suppose there is friction, then the constant force will not act in the orthogonal direction, but rather it will act in a that kind of a direction, right. In that case, what you might argue that now the constant force is doing work, yes, and that is why in such situations we will break up the constant force into a component orthogonal and a component in the direction of the motion, and the one in the direction of motion is caused by the friction, okay, and we will include it in this term because it is caused by friction. It is not really a constant force. The constant force is the one that is orthogonal to it, and it does no work, clear. So, even if this body is applying a force on this body which is in that direction, we will break it up into the constant force part and the non-constant force part, and the non-constant force part, the one that is due to friction, will be included as in the given forces FGA. Okay. So, we are still happy, constant force is doing no work. There are situations, for example, where is that? Yep. Like this, it is being moved. Is it now true that the constant force is not doing any work? Imagine carefully. Here the point of suspension is being moved like this, and the fellow is it always true that the fellow is moving in a direction that is orthogonal to the to the string? Might not be. Then what? Then what? Then that is the mathematical nicety that Lagrange thought of. He said that at any specific position of my point of suspension, at any specific position, this bob has some admissible motion. That means, if it is like this, it can only move in that direction which is orthogonal. That is the orthogonal, that is the admissible motion, admissible displacement. So, in a given position, this bob always has a specific admissible direction, admissible motion. So, even if it actually moves in a direction that is not always orthogonal, but it has a specific admissible motion, and that admissible motion always is orthogonal at every point of time, is orthogonal to the constant force. So, he said, okay, take a camera and freeze it. If you freeze it, at every point of time you will see that individually at every point of time the admissible motion is orthogonal to the constant. Okay. So, take freeze shot, at every moment of time that is happening. So, when we talk of this kind of admissible motion, that means at every point what is the direction it could move? that is admissible motion. Whether it does move or not, that is a different issue, but it could move in that direction, and that is something that is called admissible displacement. In some books you will find the word virtual displacement, but virtual often gives rise to some confusion among the students. So, I prefer to use the term admissible displacement. So, what is the technical meaning? That at any specific point of time, given a specific constant, what is the possible direction of its motion? So, that is the admissible motion, admissible displacement, and that is given by the symbol delta. So, if r is the position coordinate, then delta r is its admissible motion for the jth body delta r j. So, this is
this admissible motion takes into consideration both the motions, right? When this is moving and this is moving, the ball is
no.
moving and this is also moving.
Yes, but admissible motion is related to instantaneous position. So, if this fellow is moving, the bob is also moving, that is okay. But then freeze it at any point of time. Here is the string, and therefore, this is the direction of the of the constant force. In this position, in which direction can the ball move? Ball can always move in orthogonal direction.
But when I am freezing it, I am sort of taking this motion out of the picture, but
Yes.
this is not the actual case.
Yes, that is not the actual case, but at every point of time, that is true. Every point of time, if you freeze it, it can only move in that direction. Again, at some other point of time, let it move. Again, freeze it, it is here, but it can only move in the direction that is orthogonal to the direction of the string.
But with respect to the previous position of the
Yes,
ball,
it is moved.
yes.
Yes, it is moved. True. That is why it is a conceptual nicety. It is not immediately visible. He says that at every point of time, take time instants separately. Freeze the shot. Then look at the bob, look at the string, and say which direction could it move. Then you will find that at that moment it can only move in the direction that is orthogonal. So, even though it is not moving in the orthogonal direction, from this conceptual nicety you see that at every moment of time, individually taken moment by moment, it is always moving in the direction that is orthogonal. So, that means this delta rj has to be taken at every instant of time, and that is not same for this instant and that instant, it is different. Okay. Where was it? Here. So, we were here from the Newton's equation. In order to talk in terms of the work done, what you have to do? You have to, this is a force, that is a force, just multiply by the admissible displacement, that is the work. So, multiply both sides by the admissible displacement, what you get is times this is the admissible displacement is equal to why double dot? No, this is delta rj. So, you are multiplying it by just the delta rj, which is the admissible displacement. Here is the force, here is the displacement, and therefore, this term is work. This term is also work, but the right hand side is 0, because here we have multiplied the for the rth body the constant force times the admissible displacement, that is always 0. So, this in the right hand side is 0. We have completely got rid of the constant force from the formulation. Okay. You might argue that we still have a troublesome quantity here. You have got rid of this, but we have brought in this admissible displacement. We have to do something about it. Yes, we will do something about it. Sure, but then we have been able to get rid of the more troublesome fellow, and then we will do something about this. Okay. Now, do we have time? Yes, another 10 minutes. So, let us get to the next conceptual step. Keep this equation written in your copy. This left hand side equal to 0. That is what we have arrived.
So, will there be n equations because you have taken admissible motion of only j? I mean multiplied.
No, we have added up. For each one, it is 0. N number of zeros added up gives 0.
Summation is outside the multiplication.
Yes. So, for each one it is 0, and for n number of zeros added together you get 0. So, in the right hand side you have 0. But then remember, it was a conceptual quantity. It is something that is not actual motion. Remember, this is not actual motion. This is the virtual, or in books you will find virtual displacement. I prefer to call it admissible displacement. You will find in some books also admissible displacement. So, at every point of time this is the admissible displacement. Now, what was the next problem? The next problem was that holonomic constants offered you an advantage that you can reduce the number of equations, but there was no systematic direct way of doing that when it comes to the Newton's laws. So, we needed to do something about it. Now, if say normally the configuration space will be some n thrice n dimensional, but in order to facilitate our visual concept, let us draw a 3-dimensional configuration space. And the constant equation gives what? A surface in this 3-dimensional space. Clear? It will give a surface. For example, the motion of the pendulum gave a spherical surface on which it had to move. Similarly, for a different situation it will be different, but always it will be a surface, because a surface is what has the n minus 1 dimension. So, it will be a surface. Suppose it is a surface like this. Can you see a surface like this? There is no reason for it to be a straight surface or something like that. But then the motion in the configuration space is always constant to the surface. Therefore, the next conceptual step is to define a new coordinate system in this this smaller surface, smaller dimension surface. What will it look like? It will look like, we will say on this, let this be the origin, and let this be one coordinate, and let that be the other coordinate. And then supposing the actual position is somewhere here, we will say fine, since this actual position is always on this constant surface, we can resolve it into components in these directions, and therefore, it has this much of this new coordinate and that much of this new coordinate, that defines the position. Clear? So, we are now taking the next conceptual step of going from one set of coordinates to another set of coordinates in a smaller number of coordinates. Okay. Clear? So, initially you had the x1, x2, x3 coordinates, but now we are going into a smaller number of coordinates, let that be called q1, q2, q3. Fine. So, the number of q's would be that many less than the number of x's as the number of holonomic constants. We have established that. So, we are going from the x coordinate system to the q coordinate system. Fine. And that would be given by some kind of a transformation equation where the x k can be expressed as functions of q1, sorry, q2, q3 to qn and possibly also time. So, that is the coordinate transformation equation. Imagine that in case of a equation like this, in this case, the new set of coordinates q's are the theta and phi, because that uniquely specifies the position on the constant surface. Original set of coordinates was x1, x2, x3, xyz. Now, here we are trying to express x1 in terms of theta and phi, x2 in terms of theta and phi, x3 in terms of theta and phi, and that is what I have written here. In general, it will be expressible in this form, right. And since each of the bodies are given by some kind of a r coordinate r, we were writing things in terms of r, the radial vector. So, this will be thrice n times, but we can simplify it by writing n equations r. R1 will be then a similar function of q1, q2, qn t. Similarly, R2, the position of the second body, will be and to R n, nth body, have you understood what we are doing? So, each body was given in the old coordinate system by an r. Now, this r is expressed in terms of the new coordinate system q1, q2, q3, and maybe it can also be a function of time. If it is a holonomic constant, therefore the surface is also time variable, then it will be a function of time. So, in general I have written like that, but that might be a bit difficult to conceptualize. So, you might say that okay, R1 is expressed as a function of the new coordinates q1, q2, q3 and qn. Okay. Then we have this equation. In general, in short, we can write R j is equal to R j q I comma t. Simple, short expression of what we have written here. The jth radius vector, radial vector from the origin to the jth mass point is expressed in terms of the new coordinate system and time. Okay. If that is so, then how do you express R dot j? Because R dot j was representing the velocity, we need to convert the velocities also. So, R dot j will be drj dt, then it has to be written as a chain rule. As a chain rule, it will be sum of I is equal to 1 to the number of n is the let me write somewhere, the number of bodies were capital N. So, number of configuration coordinates was thrice n, number of holonomic constants were h, this is or small n the number of new coordinates that we need, and that is what we are writing in terms of that 1 to small n, and then it will be partial derivative of r j delta q I q dot I plus delta r j, okay, chain rule. Fine. Okay. We will stop here and then we will continue with this in the next class.